Good afternoon. We're talking about analysis of univariate data, and we look at the first set of measures which are called as measures of central tendency. In the last class, we have talked about measures of central tendency. We understood why the requirement of such measures, what is the definition, and what are the different types of measuring tendency. And we also learned how to compute it for three categories of the data: raw, discrete, as well as continuous. Now moving ahead, we talk about next set of measures applied for statistical data, which are measures of position. They are also called as partition values. So just by looking into the name here, you can say they are specific values of x at certain position. So here you are interested in position and that value of x which is in a particular position. So those values of x divide the distribution into various parts. Therefore, they are also called as partition values. And the statistical name for that is quantiles. Quantiles. Quantile means the particular values of x which divides the distribution into various parts. Now, of the possibilities, we talk about the cases, or simply I could say the values of x which divide the distribution into equal parts. Divides the distribution into some equal parts. Now, based on how many parts you require, you define various such cases. Now, we commonly use 4 cases here. You could have many such cases. The first one is median, second one is quartiles, then we have deciles and percentiles. Now, these are important because when you look into the distribution, raw or continuous distribution, you could have the presence of some values called as extreme values, which do not seem to fit into that particular distribution of the data. So in that case, we have to try and eliminate the possible extreme values from the data. And when you arrange the data in the increasing order, which is statistically called as array, you will have extreme values only present in the beginning as well as at the end. Now, somehow you could compute the values, like say you are removing 10% on either side of the distribution or 5% on the other side of the distribution. So you need the cutoff value of x. So if you have certain x values, you say I'll consider from x3 to x10 or x2 to x8. So you need the particular values of x, and those particular values of x are generally called as quantiles. There are 4 cases of quantiles, so don't get confused between these two. A quartile is a special case of quantile. So when I say median, so we are almost familiar with median. It is the middlemost value. So if you pick the middle number, the middle value is such that it is dividing the distribution into 2 equal parts. So if you just want to divide the distribution into 2 parts, you will cut the distribution at a value of x, which is called as median, and that is logically obtained using the definition, which is middlemost value. Certain times you need to divide the distribution into 4 equal parts. In that case, we talk about measure called as quartiles. Now, quartile has much importance in the statistical data, and also it has applications in the further analysis. So based on this quartiles, we'll try to look into the other properties and behavior of the data. So these quartiles are basically 3 points. And if you imagine that a distribution has so we have a distribution that is it is easily understandable if I take some raw data. So I have some observations, say 20, 22, 24, 28, 35, 56, and so on. So I have written that in the increasing order. Now I want to divide this entire set into 4 equal parts. And just imagine that you are cutting a straight line into 4 equal parts. So what do you do? First, you will make a cut exactly at the middle. We'll get 2 equal halves, and every half is further divided in their midsection to generate 4 equal cuts. So basically, we did only 3 cuts. Therefore, 3 points are sufficient to break the entire distribution into 4 parts. So I'll pick 3 values which divides the distribution into 4 equal parts. And if you look into the percentage of observation below these points, so your first cut is such that it is covering 1:3 ratio of the distribution. So it has 25% observation towards the left and remaining 75 towards the right. So these particular quartile values are indicated as Q1, Q2, Q3. So this is called as the lower or first quartile. This is middle quartile, and this is upper or third quartile. If you look into the mathematical property of your quartile, that is same as median, because median is also middlemost value. Q2 is also middlemost value of the distribution. So mathematically, the value of Q2 will be same as median. So what are we doing here? We are identifying the value of X, which are dividing the distribution into 4 equal parts. Let me take an example and make you understand. It will be very easy to have a mathematical situation to understand the data. So I have some data like this, 2, 4, 6, 8, 10, 12. Then I have to pick the points which could divide the distribution into 4 parts. So first I'll pick the middle number, which is Q2 or median. So I have value of Q2 as 8. Then I have got 2 parts. I'll further pick the middle number there. So I get Q1, 4, and this is Q3, which is equal to 12. Now, since we are looking into the position as well as the value of X, it is important to arrange the data in the increasing order. And whenever you talk about obtaining the measures of positions or quantiles, the first step is arranging the data in the increasing order. So if you use the decreasing order, the values will get swapped. So it is better to use the increasing order. Now I gave you n is equal to 7 here. And if you look into that, 7 plus 1 is 8, which is a multiple of 4. So whenever you have n plus 1 as a multiple of 4, obtaining the particular values of X as quartiles become easy. But the moment when you have n plus 1 not a multiple of 4, say for example, I have another observation, then it becomes, some mathematical calculations must be there in order to obtain those values. So it is again logically observed as the case of median. So when I say there are even number of observations, you will get 2 middle numbers, take the average of that. And here also you have 2 middle numbers, but it is not exactly the middle because we are talking about first quartile. First quartile, that it should cover 25% of the observation on this side and 75% observation on that side. And using this exercise, so we have understood that if I have n plus 1 observations, or if I have the term n plus 1, that could be easy to pick up the position values. So you can invest some time and observe why not n, why n plus 1. And based on this n plus 1, we give you the formula for raw data, like your quartile is given by I into n plus 1 by 4. Instead of giving you several formulas, I can just say, I can give a common formula for all Q1, Q2, and Q3. I indicate or I call it as Qi. So you take I is equal to 1 to produce Q1, I is equal to 2 to obtain Q2, I is equal to 3 to obtain 3. So what are the steps here? First, you will arrange the data in increasing order, and then you compute the position. So whatever the formula I have given, position is this. Now after computing the position, pick that value of X present in that position. If your position is integer, it is easy to pick the number. If the position is decimal, analyze where in between what two values it comes and pick that value with the respective proportion. We will understand again those computational steps with an example. Now coming to the applications of quartiles. Quartiles are very important if your number of observations is really large, and if you feel that you have extreme values, most of the people what they do is they only consider the data from Q1 to Q3 by chopping the 25% of observations on either side of the distribution, provided your n is large. When I say n is large, you should have really hundreds and thousands set of observations. Only in that case you can go and just consider this. So this part or this range, which is in between Q1 and Q3, that is called as interquartile range. That is range of observation in between the quartiles. So that is mathematically defined as Q3 minus Q1, and it has much of the applications in observing or deciding whether a particular value is extreme or not, and is used in chopping the data. Okay, one of the application is that. Now we look into various other properties like skewness, kurtosis, and one such measure of skewness is also based on quartiles. So quartile is important. It has its own application in measuring various other properties of the data. So this is the formula for raw data. Expanding the same case for the frequency data, discrete frequency data, will know that our f is actually indicating the position as well as the number of times a particular value is repeated. So the procedure here is same as that of your median. So to obtain median, first step will compute LCF, and then we pick the value of x value with LCF just greater than n by 2, because we are looking into the middle value. That's why we say n by 2. But here we are not looking into middle value. We are looking into the value which is covering first 25%, value which is covering second 50%, the value which is covering the first 75%. So the formula for quartiles in case of frequency data becomes I into n by 4. And some authors say you could go ahead and take in plus 1 by 4, where your n is total frequency, but we observe no much difference in the cases, and I have a habit of sticking to n by 4. So the procedure is same now. If you want your Q1, you will compute 1n by 4. If you want Q2, you will compute 2n by 4. If you want Q3, you will compute 3n by 4, and pick the LCF, which is just greater than n by 4, 2n by 4, and 3n by 4, and pick the respective value of x to obtain Q1, Q2, Q3. And coming to the continuous case, we have class intervals given to us. So this is the formula for discrete frequency data. So we say Qi is the value of x with LCF just greater than in by 4. Now coming to the continuous frequency data, we have a formula similar to that of median. So Qi is equal to L plus in by 4 minus Cf divided by f into h, the same as that of the median. But in case of median, we say the position is n by 2. Now if you want Q1, you will take this as 1n by 4, Q2 2n by 4, and Q3 3n by 4, and identify the respective class interval where that particular quartile value lies, and that will give you lower limit, class frequency, class width, and this is the LCF of the previous interval. So by substituting the values, we obtain the values of quartiles. Now extend the same definition, same concept from quartiles to the next measure, which is decile. So we talked about a value which divides distribution into 2 parts. In the second case, we talked about the distribution which divides into 4 parts. Then we talked about the distribution, set of values, which divides the distribution into 10 equal parts. So decile indicates 10 and percentage indicates 100. So we are now talking about those values which divides the distribution into 10 equal parts and those values which divides the distribution into 100 equal parts. And we observe that 1 point is sufficient to divide the distribution into 2 parts. 3 points are sufficient to divide the distribution into 4 equal parts. Now, if I want to generate 10 equal parts, then 9 points are sufficient, and similarly, there exists 99 points where the distribution could be divided into 100 parts based on those cases. So, just by looking at the definition, you will see that application of deciles and percentiles comes into picture if you have at least 9 points or 99 points given in the data. But we could just apply the definition, and even for a case where your n is less than 9 or n is less than 99, we could obtain the partition values. But it is not, those are not admissible and they are not statistically valid because you are thinking of dividing the distribution into 100 parts, then naturally there should be more than 100 values. Only then you could talk about dividing the distribution. But if you only have 5 points, dividing those 5 points into 100 parts is not that mathematically valid. But since you have a formula, you can always come up with an answer. But the application and the generalization or understanding what exactly that value is telling us, those things becomes very difficult. Okay. Now you can extend the same formulas as given for quartiles for the deciles as well as percentiles. So what we did here, we said quartiles are those values which divide the distribution into 4 parts. So everywhere in the formula you have denominator divided by 4. Now change the denominator to 10. You will get the formula for decile. So ith decile is given by I into n plus 1 by 10th value of x, where your I can go from 1 to 9. So if you want d5, take d5 as 5, I as 5. So get d5 is equal to 5 into n plus 1 by 10. And if you look into the value d5, so mathematically you can see that your 5 into n plus 1 by 10 is same as n plus 1 by 2, which is producing the middlemost value. So mathematically, your median, second quartile, fifth decile, and 50th percentile are all the same values of x. Now coming to discrete frequency data, so here also the formula is same. It could say di is equal to the value of x with LCF just greater than I into n by 10. And similarly for continuous frequency data, we get di is equal to L plus In by 10 minus cumulative frequency by frequency into h. Now just change this 10 denominator 10 to 100. That will produce the formulas for your percentiles. So for raw data, percentiles are indicated by pi. So it could be I into n plus 1 by 100. For discrete frequency data, pi is equal to value of x with LCF just greater than In by 100. And for continuous frequency data, pi is equal to I into L plus I into n by 100 minus Cf by f into h. So if you remember quartile formula, easily you can write the formula for deciles as well as percentiles. Only changes in the denominator number. So you have 4, replace it by 10, replace it by 100. And also the computational methods are also very easy and similar to that of quartiles. Now the reason why we talk about this deciles as well as percentiles is that when you have really less number of observation and decision based on only quartiles will leave you only with the 50% of the data. So as said, you can chop the first 25%, last 25%, then you are just left with 50% of the data. Now every data, every number collected has some characteristics or it has certain contribution towards the characteristics of population, and we are missing out 50% of the data. So some people say that instead of chopping 50% whenever you have less number of observations, In that case, instead of using quartiles, you can take the decision based on your deciles or percentiles. So if you're looking into P5 and P95, then you're just losing 5% of the data. So if you cut the data at first 5%, last 5%, we will have 90% of the data with us so that we can look into the calculations. So even if you feel that losing 5% is also risky, or you're not, that's not affordable, in that case, you can talk about chopping 2% on either side by taking the second partition value and the 98th partition value. Now, similarly, you can take the decisions based on deciles and other quantile values. So, of these cases, most widely used are median and quartiles, and deciles and percentiles also have their own application when it comes to the measures like kurtosis, but we'll look into the applications of median as well as quartiles. Now, I'll take the problem when we talk about the next set of measures. So this is about the second measure, which is position, measures of position. So we talked about central tendency. So here we are representing the entire set or the mass of the data by a single number. So most of the measures are based on all the values, but here we are looking into particular values of x, and we are completely leaving other values of x. So the measures of position are not based on all the values of x, not based on all observations. That is one of the major demerit of this measures of position. And then coming to the next case, we have measures of spread or measures of dispersion. So why do we need this? What are the meaning of this? Now our objective is to do some research work. So I have an objective, and in order to satisfy that objective, I have collected data. My data to be called as statistical data and to apply the statistical methods and tools and techniques, certain conditions has to be satisfied, and we look into the data and we say whether it is actually statistical. So in order to see that, we have to look into such measures. And in the coming classes, we'll talk about a distribution, frequency or probability distribution called as normal distribution. And much of the tools and techniques available in the field of inference, statistical inference, are only based on the assumption of normality. So I have to see whether my data is normal. In order to do that, we need to observe the values, various measures like this. Now, on the other hand, if you have come up with two data sets, so I have data set 1, data set 2, and now you have a dilemma, which one should be used for my research. So all the properties are satisfied, say they are statistical data, much of the properties are satisfied. So both are, equally in size as well as other properties, but you have a question, which data to choose. So we are talking about a situation where we want to compare several such data, and statistically these are just called as distribution. So I have distribution 1, distribution 2, distribution 3, and so on. Now you have to make a comparison between the distributions, and you have to come up with a distribution which you can call as an ideal distribution, or a good or a consistent or uniform data. And in order to look into these particular properties in the data, we need additional measures called as measures of spread and variation. And you can say that you can decide this based on the central tendency also. So if you have most of the central tendency values like mean, median, mode are closer to each other, then also we say there is less variation in the data. But it could happen such that all your distributions have equal mean as well as median and mode. So here also mean is equal to 20, median is 20, even in this data it is 20. So in that case, again you have a dilemma, which distribution to select. So in such cases, we talk about measures of spread. And what is this measures of spread or variation? So the mathematical term is actually the distance here. So we are looking into how far or how close the x values are with each other and it is difficult to obtain such. So if I say what is the difference between each and every value, you can compute that, but mathematically that becomes a tedious job as well as a time consuming job. So instead of looking into with each other, we talk about the central value, because central value is nothing but all the values. It is the summary of all the values. So if I use central value, I'm just actually using all the values there. Therefore, we talk about distance. Now, distance between any 2 points. So I have learned this x2 minus x1 whole square plus y2 minus y1 whole square square root. So we use the same concept of distance, but we'll get different such distance. And here we are talking about the distance between the x values and its measure. Now, the central measure could be median, could be mean, could be mode, geometric mean, harmonic mean. So here we are looking into the difference. So mathematically, difference and distance are one and the same, and there are various functions evolved which has its own application. So if I just look into x minus x bar, and because of the property of mean, we just saw that the total of that actually becomes 0. So if I just use x minus x bar, I cannot talk about the average distance. So I should come up with certain other, techniques of obtaining this. So what we do is we take the positive quantities of this distance, and then we observe that the total is not zero. And for that, I could divide, obtain the total, I could divide it by n, and we call this as average distance between x and x bar. So this is called as an average deviation or mean deviation. But one of the major drawback of this is that you are ignoring the negative sign just by considering the modulus of the value. You are familiar with this modulus operator, right? The operation modulus just removes the negative sign if at all present in the number. So any negative number under the mod operation is treated as positive. By default, if you already have a positive number, mod of that produces positive. So mod is defined such that if you take mod for any x, either negative or positive, that always produces a positive x. So this is just an introduction to the distance as well as the average. But when we look into the various cases or various measures, they are broadly categorized into two cases: absolute measures as well as relative measures. Now, the major difference is that now we are in a situation where we are comparing several distributions. Now, distributions could be different based on the units of measurement, based on the time of collection. So if you are, want to compare the distributions which have the same unit of measurement, like say you have taken the two set of marks, maybe say marks of first BSc for the past 5 years, marks of second BSc for the past 5 years. So both the distributions are same almost with respect to the properties. So unit of measurement is same. So in that case, if you want to do some comparisons and come up with a distribution, we'll be using the absolute measures. The reason is whatever the measure you define under this scenario or category, they carry the same unit of measurement of the data. So if your x is in terms of kgs, your measure will result in kgs. If it in centimeters, it will result in centimeters. So that's what we observed even in the case of central tendency as well as position. So this could be used when you're comparing distribution with same units of measurement. As said, you have distribution 1 marks, distribution 2 marks. So you can use these measures in order to bring the comparisons. On the other hand, if you have a set of distributions where the unit of measurements are different, like say you're talking about weights of say students here, and you're talking about height. Now you have to see in which case the consistency exists or uniformity exists. In that case, using these measures doesn't help you, because you cannot say 2 kg is less than 4 centimeter, or such mathematical conclusions cannot be done. So we have to come up with a measure which doesn't carry the unit of measurement, so that if you have pure mathematical numbers, real numbers, then the comparisons could be easily made. So we define another set of measures of spread, which are relative measures, and they doesn't carry the unit of measurements. The unit of measurements are free. Now, based on the requirement as well as type of the data, so again we define much of the measures here. The first simplest measure is range, which gives you a knowledge about what is the entire spread. So where the data starts, where the data ends, and what is the span of the data, that is given by this measure called as range. Now, since you have highest value, say in terms of kg, lowest in terms of kg, and difference of kg is also kg, so this carries the same unit of measurement. Next, so if you look into the applications or much about this, it is very easy to understand, but it doesn't give you the exact, say, essence of measure of spread. It just on average says where the data is starting and ending. So that could be based on just highest and lowest. And if you have very high number in the data, very low number in the data, the range gets affected by the extreme value. Say, for example, if you talk about cases like this, and again you have the case like this. So almost in most of the cases, the data points are similar. But if you look into the range here, it is 7, 8 minus 1. But here it is 100 minus 1, 19. So this is because of the presence of the extreme value, which is 100. So we say range is much affected by extreme values. So hence it has very less statistical applications. We'll just look into, we use this whenever we want to see what is happening to the data on a whole. So we need to classify the data or obtain the frequency distribution. In that case, we'll look into the application of this. Now, since range is much affected by the extreme values, we talk about the range within the quartiles, which is IQR, interquartile range. So as said, the first step here is you compute Q1, Q2, Q3, observing what the type of the data is, whether it is raw, discrete, or frequency data, and then compute IQR by the formula Q3 minus Q1. Now, since your quartiles are also the specific points of X, they carry the same unit of measurement, and the difference also carries the same unit of measurement. Then we also talk about quartile deviation. So range is telling you, the IQR interquartile range is telling you what is the first quartile, what is the third quartile, and how far you are observing the data within that. But what is the actual deviation between them, the average case? In that case, we look into the formula Q3 minus Q1 divided by Q2. That is the quartile deviation. There are several other measures. The next commonly used measure and most widely used measure is standard deviation because of its simplicity as well as involving the computed arithmetic mean, and it has the square root function as well as square function which smooths the curve mathematical function. So it has wide application. Standard deviation, and for raw data it is given by the formula sigma x minus x bar whole square divided by n and the square. We'll come back to this. We'll see how to compute this, what is the simplified form, what happens when frequencies are there, why we need standard deviation, how it helps. We'll look into that in detail. So at this time, you'll just see that you have a measure called as standard deviation that is under absolute measure, and that uses the concept of arithmetic mean, and it is most widely used. So if any person who has very little knowledge of statistics, if he is talking about a measure called as central tendency, which he just calls as mean, and he is talking about the measure of spread or deviation, then that means that that person is talking about arithmetic mean as well as standard deviation, because they don't have the deeper knowledge about the data, extreme values and all. So just they know if you have been given with a set, how to compute the average arithmetic mean, how to compute the standard deviation. So that's why most of the fields of applied science like demography, or it could be the science called as say psychometric, biometry, biology, as well as medical science. In all those cases, means and standard deviations are most widely used. And one of the other measure which I already defined is called as average deviation or mean deviation, and here we call it as the average of the absolute distance between any average and the average of that. So you take any average, it could be mean, median, mode, obtain the mode of the distance, take the total, take the average. Now, since we are talking about sum of something as well as the average of that, this is called as average or the mean deviation. And as said, you could use your mean or median or mode, and you could come up with three such measures, which are mean deviation from mean deviation from median, and mean deviation from mode. We'll not look into the deviations from geometric mean and harmonic mean, so need not worry. So I'm using arithmetic mean to get the differences. Therefore, it is sigma x minus x bar by n, and here it is called as average deviation from mean or mean deviation from mean, given by this formula. Instead of using mean, if you are using median, then you get average deviation from median, given by this. And if you look into the data or the formula for frequency case, it will be summation f into mod x minus x bar divided by sigma f. So it is the total of this. So please write the mod symbol correctly. Don't use use the curved line there. It should be two straight line. And if you replace that measure by mode, you get mean deviation from mode. And whenever you compute the deviations for some raw or discrete frequency data, you will always observe that the mean deviation from median is the least compared to the other two, compared to MDX bar or MDZ. So we'll observe this MDM to be very least. So these are the 5 absolute measures of dispersion. So we'll look into the calculations, numerical problems on all these cases. As said, you can use this whenever you want to come up with a measure of spread, and you have to select one distribution which you can call as an ideal distribution or ideal set of data when the distributions have the same unit of measurement. Now, for each of these measures, we try to obtain a measure based on this only, but such that it produces a unitless measure, and those are called as relative measures of dispersion. Relative measures of dispersion. For each of the cases, we could just simply obtain a coefficient. And most of the measures what we define as unitless measure in the field of statistics, they are termed as coefficient. So very such measure for range is coefficient of range, that is given by the ratio difference over the sum of the highest and lowest value. So if you just obtain H minus L, it is range. H minus L is in kgs. If your X is in kgs, H plus is also in kgs. So when you divide kg by kg, the unit get cancels. So you will get a unit-free measure. So, but we look into the application of this very rarely. But as said, if you are looking into the case where you are only interested in high and low values, say you're talking about price of gold, price of stock values, where you are interested in what is the maximum by the end of the day, what was the minimum in the day. In that case, you can talk about range as well as coefficient of range. Now, coming to the second case,